Hello students and welcome to lecture 4 of unit 3. In this lecture we will discuss diamagnetism and paramagnetism. So, electronic configuration plays a very important role for understanding the magnetic properties of an atom. Let us review electron configuration once again. So we know electron can be imagined to be residing in specific locations, where orbital is a one electron wave function, okay, and each orbital we say can have at max 2 electrons in it, both having opposite spin. Now how the electrons fill the orbital is determined by several laws. The most prominent of them that we use is the Hund's rule, which states that every orbital in a sub-level is singly occupied before any orbital is doubly occupied. That means first one electron occupies the orbital and after that the other electron follows. Also, all of the electrons in singly occupied orbitals have same spin to maximize total spin. That is, orbitals follow the maximum multiplicity rule. Now, when there is one electron in 2p orbital, the electron fills in this 2px orbital. If there are two electrons and for 2p orbital, these levels are degenerate and hence first it is filled in 2px and then in 2py. When there are 3 electrons, all the orbitals are equally filled. Now, when there is an incoming of the fourth electron, then the fourth electron will change its spin, will go into the opposite spin and enter into the 2px orbital. Again, when there is a fifth electron, it will further occupy 2py orbital, and as such there is the electron configuration of all atoms. Also, the arrows show whether the electrons are pointing up or down. That means the spin is clockwise or counterclockwise. So spin is dedicated by the arrow. Now Pauli's exclusion principle again states that electron filling the same orbital must have different spins. So if different spins and no two electrons can have the exact same quantum number. Now see here, if we fill the helium 1s2 orbital by filling the orbital with 2 electrons of the same spin, this is the wrong representation. Same happens if we give both in the downward direction, both in the opposite direction. This is not how electrons are represented in an orbital. The correct way is one electron is in one spin and the other electron is in the opposite spin. So, because Pauli's exclusion principle states that no two electron can have the same set of quantum numbers. So here the spin quantum number varies. What is paramagnetism? Paramagnetism results from presence of at least one unpaired electron spin. That means there must be at least one electron which is not paired in the atoms or molecules. Okay, so any material that possesses atoms with incompletely filled atomic orbital becomes paramagnetic, and the spin of the unpaired electron gives them a magnetic dipole moment. That means they are scattered like this in absence of an electric field. Whenever there is a presence of an electric field, all this spin they orient along the direction of the magnetic field. So when there is an unpaired electron, that unpaired electron basically acts like a tiny magnet in that material. That is why in presence of an external magnetic field, that particular electron having a property of a tiny magnet will align in the direction of the field, and all unpaired electrons will align in the same way, and that is why a paramagnetic material is attracted in the magnetic field. When the external field is removed, suppose the field is removed, then their spins are again in random orientation. They again go back to their original form. Again, let us see for example titanium. Titanium electronic configuration can be written as argon 4s2 3d2. If we elaborate, expand the electronic configuration, then we see that the 3d orbital has 2 unpaired electron. So because of the presence of these unpaired electron, titanium is paramagnetic. Now if we remove these 2 electron, then the 4s orbital, what happens, this electron will move to d orbital. Again it remains as paramagnetic. Okay, if it would have had all electrons as paired, then it would have become diamagnetic, that we will see later. So paramagnetism refers to the property of material that are weakly attracted to the magnetic field, and once the field is removed, the material lose their magnetism. Okay, so some examples are coordination compound myoglobin that you may have come across, some transition metal complexes that have unpaired electron, and metallic elements such as titanium and aluminium. What is diamagnetism? When two electrons share an orbital, their spin quantum numbers are different, that we have already established. One is spin up, the other is spin down. When it comes to determining the total spin of the electron orbital, we have to account for both the spins of the electrons. Now in order to decide whether the spin cancels out, we add the spin quantum numbers together. When the 2 electrons, suppose there are 2 electrons and their spin are paired together in the orbital, that is their total spin is 0, then they become diamagnetic electrons. That means if one is in upward direction, the other in the same orbital is in downward direction, then it is called as diamagnetic electron. So whereas in paramagnetic materials are slightly attracted in the magnetic field, the diamagnetic materials are they are repelled in the magnetic field. And this chi value here is magnetic susceptibility. We will study more about this in the next class. So note when spin up and what spin up and spin down means in terms of electron sharing in an orbital. Okay, so when the electrons in the same orbital have opposite value for their spin quantum numbers, they cancel each other out, because one has plus half and the other has minus half, so they cancel each other out and there is no leftover spin left in that orbital. Suppose all the electrons in that atom, in an atom, are paired. Okay, all the electrons, be it 1s or electron, 2s electron, 2p or 3d, 3s, whatever electrons are present in it, all of them are paired and they share orbital with another electron. That means every orbital is fully filled. Then the spin total spin is 0. So the total spin in each orbital is 0, and this makes the atom as diamagnetic. Let us see here. For manganese, it is neon 3s2. Because here the spin is paired and there is no unpaired electron present, that is why it is a diamagnetic material. Whereas sodium, aluminium, silicon, phosphorus, they all have unpaired electrons and they have paramagnetic property. Because these electrons are paired, such materials are not attracted in the magnetic field, but they are slightly repelled. Such materials are repelled in a magnetic field. For example, magnesium, bismuth, antimony, there are several examples of diamagnetic material. Let us look at different types of magnetism. Although this is not a part of your course, let us try to understand what the different types of magnetic materials that can exist. So there can be 4 main categories of magnetic material. They may be paramagnetic, diamagnetic, ferromagnetic or antiferromagnetic. We have already seen what diamagnetic and paramagnetic looks like. So for diamagnetic material, in absence of a magnetic field, they are present. In presence of a magnetic field, their orientation is opposite since they are spin paired and they cancel and they are repelled in the magnetic field. For paramagnetic material, the spins are random. In absence of a magnetic field, in presence of a magnetic field, they orient along the field and they are slightly attracted to the magnetic field. And in absence of the magnetic field, they again go back to their random motion. For ferromagnetic material, however, they are already arranged in a particular direction in absence of a magnetic field, but in presence of a magnetic field, their direction changes and they align. So this is the strongest form of magnetism. This shows the strongest form of magnetism, and it is strong enough to be felt, and these remain magnetized over time. as unlike paramagnetic material that do not remain magnetized even after removal of the external magnetic field. So the common iron-based magnets and rare earth magnets display ferromagnetism. So in summary, when two electrons are paired and their spin is 0, they are diamagnetic electrons. Atoms with all diamagnetic electrons, all electrons must be diamagnetic, are called diamagnetic atoms. For a paramagnetic electron to be present, there has to be an unpaired electron. So if an atom has one orbital with a net spin, as long as it has at least one paramagnetic electron, it is a paramagnetic atom. Diamagnetic atoms are repelled in a magnetic field, and the unpaired electrons of paramagnetic atoms align in response to the magnetic field and so are attracted. Also, paramagnets do not retain magnetization in absence of magnetic field because the thermal energy present randomizes their electron spin and takes them to their initial condition. With this, I conclude today's lecture. I hope you have been able to follow what is diamagnetism, what is paramagnetism. These are simple concepts but very important in the long run. If you have any doubts, I shall be available to answer all your queries. Thank you for your attention.